Good afternoon, everyone. We're happy that you've joined us for this webcast, and we're excited that this is the first of many that we offer during our annual Design Innovation Month. My name is Kurt Curtin. I'm the Technical Manager for Simulation Products here at Computer Aided Technology, and I'll be your host during today's session. I'm joined by my colleague, Alon Finkelstein, who is one of our Simulation Product Specialists and a very capable engineer with a lot of interesting experience in the design of racing yachts. Alon will be presenting the topic today, which is setup tips for advanced loads in SOLIDWORKS simulation. In particular, he's going to look at non-uniform force and pressure loading. I know you'll find Alon's presentation interesting and informative, so without further delay, I'll hand it over to him. Alon, take it away.
Thanks for the introduction, Kurt, and welcome to all our webinar attendees out there, wherever you may be. The topic of today's webinar is non-uniform force and pressure loading in SOLIDWORKS simulation. So let's get right to it. So within SOLIDWORKS simulation, there's basically two types of force or pressure descriptions that we can use. So the first one is a uniform loading, which I'm sure is pretty familiar to most of you out there. So in this case, a load is applied with constant magnitude. In other words, there's no variation in magnitude over the entity. And some examples of that include, the weight of an object. Think of just a box sitting on a table or something like that. Or a bolt clamping force. You torque up the bolt to a specified value, and it clamps the two parts together, and there's no specific variation. So a corollary to that is a non-uniform loading. So let me describe that in some detail. In this case, the load varies based on a user-defined equation. And the equation is a function of position or potentially angle, depending on the coordinate system. And the coordinate system used can be either Cartesian, cylindrical, or spherical. And some examples include hydrostatic pressure in a fish tank or something like that, or perhaps a dam wall, or airflow around an object. So if you look at our little diagram on the right where we've got our fish tank, and we've got hydrostatic pressure, and we know it has a linear variation relative to depth below the water surface. So the coordinate systems available in SOLIDWORKS, we have three kinds. So Cartesian coordinates, basically we can specify the location of a point with three distances, x, y, and z. I'm sure this is familiar to everyone. And then in a cylindrical coordinate system, we specify the position on an object with a radial distance r, think of a radius, a circumferential angle t, and an axial distance v. And then in spherical coordinates, we have one distance and two angles. So we have a radial distance r, a longitudinal angle t, and a latitude angle p. So the longitudinal angle t is sort of the angle measured from the x-axis to the y-axis, and the latitude angle p is measured down from the z-axis to the xy plane. So let's have a look at some worked examples of how we would use this in SOLIDWORKS simulation. So the first example we're going to look at is pressure as a function of depth in a fish tank. So I'm sure you're all familiar with the just hydrostatic pressure equation. Pressure, as it varies with depth, is rho GH, rho being the density of water in this case, G being gravity, and H being the depth below the free surface. So let's switch now to SOLIDWORKS and have a look at a worked example of this. So here's our fish tank assembly. It consists of a base unit, a tank subassembly, a cover subassembly, and then there's water inside the tank. So that's our geometric, our CAD model. So let's go have a look and see how we set this up in simulation. So within our little parts tree here, so we're not actually interested in any stresses or deflection of the base or the cover. So what we can do is go ahead and exclude those from the analysis. So you can see, this is our base part, but we've gone ahead and excluded it from our analysis. The same with like the cover subassembly. So we're only looking at the tank. So in this case, the tank is made up of a couple of plastic rails. So these are made of ABS plastic. This is the lower one, and this is the upper one. And then we've got the walls of our tank, and those are made of tempered glass. And I've actually gone ahead and split the glass into like a lower portion and an upper portion, and I'll describe in a minute why I've gone ahead and done that. And the split line is coincident with the top surface of the water, the free surface of the water. So moving through our setup a little more, we've got a global bonded contact to join all our parts together. Pretty simple in this case, that's all we need. In terms of fixtures, so the way we've gone ahead and fixtured this is first we have an on-flat face condition to the bottom of the tank. So that's specifying that the bottom of the tank cannot move globally in the global Y direction. But obviously the tank can still sort of slide in X and Z, so we need to restrain those degrees of freedom. So the way we do that is we come and select this lower left corner vertex here and give it a fixed geometry constraint. So that restrains it in X, Y, and Z. But now you can imagine the whole tank could still potentially hinge or rotate about this edge here or about this vertex. So we need to stop it spinning around that vertex. And the way we do that is with a reference geometry constraint. So we pick this vertex in this lower right corner, and we tell it that relative to this face here, we are constrained in that direction. So we can't move relative to that face at all. So that stops it from spinning around. Then let's look at our external load. So in this case, the load of interest is our pressure load. So this is applied to the inside faces of the tank, including the bottom surface. So those are selected over here. And it has a value, recall it's rho GH. So rho times G is 9.81 times 1,000, so 9,812 newtons per square meter. So that's our sort of nominal value. And then we need to give it its dependence with the depth below the water surface. So the way we do that is there's a little button in SolidWorks, this non-uniform distribution button. We click that. The first thing we have to tell it is give it a coordinate system. So what we have is a coordinate system right at this vertex here, which is the location of the top surface of the water. That's the origin of our coordinate system. It's a Cartesian coordinate system, which we specify by selecting this button right here. And it has Y going down, sort of aligned with this edge. And then next we need to define our equation for how our pressure varies with our coordinate system. So we use this edit equation button right here. And in this case, it's a very simple equation. Basically, it's rho GH, H is the depth, and in this case, because Y is pointing down, it's just Y. And recall that we're multiplying that Y value by this constant value, 9812 over here. So that is basically our pressure setup, and we can go ahead and run that. But before we do that, I wanted to just describe why we split this face. So what I've done is I've created a configuration that does not actually split the face. And I've said, well, let's apply the pressure to the entire, one entire face. And what you can see, if you do that, I have the exact same equation. It's just Y. I've created a coordinate system, midway down this edge just to illustrate the point that I'm trying to make here. And the point I'm trying to make here is that if you don't split that face, what you'll end up with is a sort of a pressure going from inside to out on the lower part of the tank below the coordinate system in the positive y direction. But once you get above the origin of the coordinate system into the negative y direction, the vector reverses, and you actually end up with essentially like a suction on the inside of the tank. And that's obviously not correct. So that's why we need to split that space. So shifting back to our correct configuration here, which is the one with the split, we've got all our setup complete, and we can go ahead and run this, which I've already done. And then we can take a look at, displacement results. You can see a sort of bowing out of the sides of the tank to the tune of about 4.1 millimeters. And then we can also look at stresses, in this case looking at the first principal stress in the bottom of the tank to the tune of about 23 MPa. Now our tempered glass is a brittle material. We don't, it's going to crack before, there's not going to be any yielding. So it has an ultimate strength of about 70 MPa. So in this case, at 23 MPa, we should be in pretty good shape. And just one last thing I wanted to point out about the setup, which I forgot to mention earlier, is just that we modeled the two rails as solids, but we modeled the glass as shell elements. And so we're getting about 23 MPa maximum principal stress in our shell elements towards the bottom of the tank. So that's our Cartesian coordinate example. So now let's have a look at a cylindrical coordinate example. And in this case, we're going to examine wind loads on a tank or a pressure vessel. So imagine we've got a 90-mile-an-hour wind coming from left to right. Imagine our tank is maybe experiencing some hurricane winds, and we want to study the stresses and the deflections in our tank. Imagine we've done maybe a flow simulation study or some hand calculations where we've calculated that the maximum pressure, which occurs sort of on the side of the tank, is right around 0.2 psi. And what we can expect is that pressure will decrease to 0 at the top and the bottom of the tank, where the wind load is essentially tangent to the face of the tank. So that's what we're trying to model, and let's go ahead and look and see how we do that in SolidWorks. So this is our geometry. Again, you can see we've gone ahead and used the like a split face command to split our tank into sort of two hemispheres, a left and a right side, because we only want to apply this pressure load to the upwind or the windward side of the tank, and nothing to the downwind side of the tank. So we've gone ahead and split our tank. So let's go ahead and study our setup here. So pretty much everything is modeled as solids in this case, with the exception of the tank itself, which is a thin-walled structure that's much more conducive to shell elements. So we use shell elements for that. Everything is alloy steel, so that's been assigned to all of our bodies as well as our shells. We've got some contact conditions to connect the parts together. For fixtures, we're basically just fixing the base of our tank to Mother Earth like that. So that's a fixed geometry constraint on the base of those support legs. And then let's look at our pressure setup. So basically we've gone ahead and selected, all of the windward side faces of our tank. So that's where this pressure is going to get applied. Obviously, as we get toward the ends here, where we've got this sort of hemispherical end on each side, this sort of pressure distribution is a bit approximate, but for what we're trying to show here, it's good enough. So we've got our maximum value of 0.2 psi, and then we need to specify how that varies as a function of our coordinate system around the tank. So we hit this radio button for non-uniform distribution. We specify our coordinate system, which is the tank center coordinate system. We tell SOLIDWORKS that, this is a cylindrical coordinate system that we're using. We give it units, in this case inches and radians, and then we edit the equation. And in this case, it's pretty simple. It's just a cosine of t, t being the circumferential angle. Recall that, so that angle goes from x to y. So when that angle is 0, would basically be on this left side of the tank. And remember that cosine of 0 is 1, so we would return 0.2 psi at that location. And once we get to plus or minus 90 degrees, which is the top and the bottom of the tank, cosine of plus or minus 90 is 0, so that gives us our 0 pressure at the top and the bottom. So that's the setup of our pressure, and we can go ahead and run this, which I've gone ahead and done beforehand, and query our results. Sorry, let me just turn this pressure off now. And you can see we're getting a very small displacement of about 1.5 e to the minus 3 inches. When we look at stresses, those are real low too, about 275 psi versus a yield strength of about 90,000 psi. So obviously this wind load is not going to trouble our tank too much, but it is more to illustrate the point of how to set up a cylindrical pressure distribution in SOLIDWORKS. So let's switch back to our presentation again and look at our last example, which is use of a spherical coordinate system. So again, we're going to look at some wind loads. This time, the wind loads are on a dome structure. We've got wind coming in from the side. Recall in our spherical coordinate system, we're going to use a radial distance r and then two angles, the longitudinal angle t and the latitude angle p. And we're basically expecting, we want maximum pressure over on this bottom corner here that faces the wind. And then once we move around the sides and also to the top, we want 0 pressure, because at that point our geometry is essentially tangent to the wind. And so the equation that gives the right distribution of pressure for that is this equation down here. Our pressure is our P naught, our maximum pressure, multiplied by sine of the latitude angle times sine of the longitude angle. So let's have a look at our setup in SOLIDWORKS. So this is our geometry. We basically got essentially a weldment structure made up of a whole bunch of pipes or tubes, and those are covered by kind of a thin surface or thin membrane, making somewhat of an igloo structure. And we've got a coordinate system defined in the middle of our igloo called a dome-centered coordinate system, just like that. So when we switch over to simulation and we study our setup, so within our little parts tree here, because we modeled all those tubes as a weldment, basically SOLIDWORKS defaults to treating those as beam elements, which is appropriate in this case. And they are made of aluminum, 6063 aluminum. And then we've got a surface surrounding that, which is a nylon material. We've got this joint group, which defines basically how the pipes are all connected at their ends. I'm going to go ahead and hide that for now. And then we've got our contact conditions that bonds all the parts together. In terms of fixtures, the way we fixtured this is basically by fixing the bottom joints that are on the bottom edge of the pipes. So those are fixed to earth. And then the second fixture that we have is applied to the edge of our surface of the dome, and so those are fixed too. In terms of external loads, we have a gravity load, which is just customary 9.81 meters per second squared in the negative global y direction. And then we've got our pressure load. So let's study this in a little bit more detail. Again, we've got a split face command to split our dome surface such that we only apply the pressure to the windward side. And so in terms of a direction, we're telling it, I want it to be normal to this right plane of our model. So it's coming in kind of left to right. Our maximum value is 0.2 psi. And our non-uniform distribution, we're going to use our dome center coordinate system. Tell SolidWorks that we're using a spherical coordinate system. Give it units if those are appropriate. So in this case, it's millimeters and radians. And then we edit our equation, and this is where we put that equation that I showed you earlier of sine p times sine t. So sine of the longitude angle times sine of the latitude angle. So that takes care of our pressure. We can go ahead and run this and query our results and show some displacement results here. Let me hide our fixtures. And I'll hide all our loads. So yeah, you can see that over on this bottom left corner where our face is normal to the wind, we get the highest displacements, somewhat expected result. In this case, it's pretty small, 0.02 inches, so not something to worry about. And then it sort of tapers off to zero once we get to the top and the sides of our dome structure where the wind is essentially tangent to the faces of our geometry. Stress plot looks fairly similar. Again, stresses that are pretty low given that we're only really applying a wind load here to our structure. So that sort of concludes the setup part of the presentation, and let me know if anyone has any questions.
Thanks, Alon. Very nice presentation of this topic for non-uniform loading. I'm sure you all found your way here by registering on our website for this webcast. So if you haven't done so already, look over the remainder of our upcoming webcasts and check those out, see if you might be interested in those. There are 3 additional ones related to simulation and many more related to general SOLIDWORKS topics. I don't see any questions at this point. Looks like everybody's good to go, Alon.
Great. Well, thanks everyone for listening, and good luck with all your simulations. And don't hesitate to reach out to us at CATI with any questions or support that you might need.